Hey guys, this is Young. I'm the SI leader for Physics 1052, Section 3. This is a testing video to see if everything works. I have my session, the SI session, online right now between, no Friday. See, I've got the first issue here. It's on Monday, Wednesday, 5 to 6:30 p.m. It's on Teams. You should get my email with the link to join. I'm having office hours, and I sort of just want to run them with these little problem-solving videos. If you have a problem that you can't figure out, take a picture, send it to me. I'll see if I can figure that out and maybe walk you through that within these little videos. So for the testing video, I would like you to pay attention to the visibility of all of the signs that I put on. Is the strokes visible enough? Can you view it from your phone? Do you want to have a thicker, or do you want it to be thicker or of a different color? Can you see what I typed down? Can you hear my voice without dialing up your phone or your laptop or your television too much? And if there's any glitches, does the screen went blank, went black, doing weird stuff, letting me know. With that being said, let's move into our sample problems. A laser beam is incident on a 45-45-90 prism perpendicular to one of its faces, as shown in figure 2220. The transmitted beam that exits the hypotenuse of the prism makes an angle of theta equals to 15 degrees. Let's just put 15 here. With the direction of the incident beam. Find the index of refraction of the prism. So we're going to find index of refraction for the prism. Okay, so I think it's pretty obvious we want to use Snell's law. I don't think there's any other laws that's applying to this situation. We've got angles, we're looking for index of refraction. Snell's law is perfect for that. So, N1 sine theta 1 equals to N2 sine theta 2, right? So it's kind of confusing. I don't know if they did it intentionally, but this theta here is neither of theta 1 and theta 2, because if we recall what these thetas are, they are the angle between the incident or the refracted light with respect to the normal. And the normal is being represented by the dashed line here. This is the surface. And the normal wasn't being drawn on this triangle yet. We're going to draw that looks like a right angle. Okay, so this is 90 degrees. This is the normal to the surface to the hypotenuse, right? This is the incident beam. It's not being said, it's not explicitly said in the problem, but I'm going to assume this is 90 degrees, or else we can't solve it. It's a 45, 90 degree angle. I'm going to put a 45 here. Let's figure out theta 1 and theta 2 first. So theta 1 is the incident light with respect to the normal. Incident light, normal, this is theta 1. And the refracted light is the exiting light with respect to the normal. Exiting light with respect to the normal, this is R theta 2. So indeed, theta is a part of theta 2. Theta 2 would equal to theta plus phi. Let's call it phi right here. Now can we figure out theta 1? Hopefully it's pretty obvious from the geometry setup. This is 45 degrees. We assume this is 90 degrees. The rest of the angle must be 45. This is 45 degrees. And since this is the normal to the surface, the angle right here has to be a 90. So theta 1 plus 45 equals to 90 degrees. Theta 1 equals to 45 degrees. Theta 1 and its opposite angle, if you get another color, if you pay attention to this crossing right here, theta 1 is 45 degrees. Its opposite angle of the crossing of this x should also be 45 degrees. There should be the same angle, and it turns out to be phi. So phi equals to 45 degrees. This is theta 1. They're the same angle, just to highlight it. Get in there. Okay. And we also happen to have this very nice expression, theta 2 equals to theta, which is 15, plus phi, which is 45, giving us 60 degrees. Right? So we now have theta 1 and theta 2, but we can't solve this equation unless we know either n1 or n2. And here's the other assumption that kicks in. I'm going to assume that the medium the light is traveling in before it hits the prism is air, or vacuum, even better. But that assumption gives us a very good starting point, because the index of refraction in air or vacuum is basically 1. Problem is, do we put n1 into 1 or n2 into 1? We can come back to this diagram here. This is theta 1, theta 2. So this is our n1, this is our n2, right? Theta 1, we have the light coming in, hitting the surface, making an angle with the normal. So we have the light coming in, hitting the surface. This is theta 1. So n1 is indeed our prism. I'm going to put P. And our n2 is, this is n2, the medium, is the place where light leaves the surface and forming an angle with the normal. So we're seeing our light leaving the surface, forming an angle with a normal. So indeed, n2 is our n air, which equals to 1. So now our equation looks like n of p, n sub p, sine theta 1 equals to, this is 1, I'm not going to write it down, sine theta 2. Sine theta 1 equals to 45 degrees, sine theta 2 equals to 60 degrees. We got n of p equals to sine theta 2 over sine theta 1. This is sine 60 over sine 45, giving us square root of 3 over 2 over square root of 2 over 2. These are just the values of sine 60, sine 45. You can check that with a calculator. I've done it a lot of times. This is square root of 3 over 2 times 2 over square root of 2, leaving us with square root of 3 over 2. For a numerical answer, I have Mathematica pulling up. It's 1.2247. Close to 1.2247. So there we go. This is how we solve a fairly easy geometry loaded example problems. Well, our emphasis is on whether you can read everything. So leave a comment or shoot me an email to see if you think there are improvements that I can make in terms of audio, video, anything. Thanks, guys.